Welcome to my lecture on the human eyes. In this lecture, I will teach you about the anatomy of the eyes, and it is important to understand that the eyes are devices of light transmission, refraction, and transduction. And although it works a lot like a camera, I'll try to convince you that they're much more than a camera. In this lecture, like in this course in general, there will be some little exercises for you to do so that you experience some visual phenomena slash illusion. And sometimes it takes a few trials before we experience them. We have to set ourselves up correctly and so on. So in this video, you are free to stop the video and do those exercises at your own rhythm. They are really compelling and worth doing, so please take the time to do them. If anything, that's the thing to do in this class. So enjoy. We are often told to not rub our eyes. Why is that? During COVID-19, obviously, we don't want to spread the infection, so it makes sense. As a joke, though, in this class, I say do not rub your eyes because they are your brain. As you know, if you hit your head and you hit the back of your head, you end up seeing stars. And the reason for that is that you stimulate the very back of your head, which is the occipital lobe, which is where neurons specialized in visions are. Likewise, although we should not rub our eyes, we all at some point did it. And when we do it, we do see some sort of light. It may be weird patterns or something, but we do experience visual phenomena. And the reason is the same as hitting your head. When you touch your eyes or rub them, you stimulate visual neurons. Right, so as you know, light is some physical energy that travels in straight line. It goes, reaches your eyes, and the light will be absorbed by the photoreceptor at the retina. And the light absorption will be changed into some neural activity that will travel to the cortex and it will go straight to the back of your head, the occipital lobe, which is the visual cortex. So when you hit your head or rub your eyes, you are stimulating visual neurons and you will experience some visual stuff. So if you do rub your eyes, be gentle. One is the light transmission. And in a few slides, we'll learn about the iris, pupil, and ciliary body. The other function is refraction, so the bending of the light. So we have sharp vision, and that's done by the cornea and the lens. We'll come back to that. And finally, the function of transduction is important, and it is the retina that is crucial for that. And the retina has two types of photoreceptors, the cones and the rods, and we'll study those. So let's start with light transmission. Okay, so let's start with the function of light transmission. So one of the very important function of the eye is to make sure enough light comes inside the eye to reach the retina so that we can have good vision. So when we are in very bright light environment, our eyes need to close a little bit, and it is the iris that closes. The iris is the colored part of our eyes, and it controls how much the opening is, more or less big. The opening itself is the pupil, and the muscles involved into this process of opening and closing the iris are the ciliary muscles. And the white part of the eyes is what we call the sclera. Now, this is an interesting fact. The movement of the iris is somewhat controlled by the autonomic nervous system. So, just like heart rate or perspiration. So, the autonomic nervous system is the system that is involved in a situation where you are either scared or the flight and fight reaction, for example, where if you're scared, your heart rate will go up and your perspiration may go up too, and you will have very automatic reactions. And one of those reactions is, in fact, when you're aroused or attracted sexually by somebody, the pupil will actually open up, dilate. So I just put there an interesting scientific American article about pupil size and emotional state. So this is a link, and so if you want to read that at your for your interest, it's interesting. A good way to know if somebody's interested in you is seeing if they have very wide, large pupil, and if they do, it's a good sign. Another interesting fact about the pupil is our pupil, as you know, is round, but not all animals have that shape of a pupil. In fact, if you look at the pupil of cats, and you will notice that they are elongated. So, in fact, the iris, so the colored part of their eyes, will close completely because of that opening being elongated. And this is very telling about the behavior of the cats because they are night hunters. So they see well. Their retina doesn't need that much light in order to see well. So they see well under low light condition. So when it's the day and it's very bright outside, their iris close almost completely so that they protect the retina from having too much light coming in. So again, the eye really controls how much light is transmitted to the retina, to the inside of the eyes, and that is very important function of the eyes, of course. The second function that the eyes are involved in is refraction. So, as you know, refraction is the bending of light so that it comes to a focal point at a specific distance. The eyes has the cornea and the lens as structures that do the refracting exercise. So the cornea is the very outer layer of your eyes, and it's bulge as you see here, and it has most refractive power, but its power is fixed, so it always stays the same no matter what lighting conditions you're under. The lens is also a refractive device. It bends light, but it does it much less. So it has much less refractive power. However, its power is flexible. So depending on your viewing conditions, it will more or less bend the light. So if you look at something very close, it will try to bend it more. If you look at something far, it will try to bend it less, and so on. A normal eye will bend the light so that it will come into focus at the level of the retina. And whatever we look directly at will be at the level of the fovea and macula in the retina. Okay, so this is the illustration of a normal eye, and if you go to an optometrist and your eye does a good job at refraction, as illustrated here, you will end up having an acuity of 20/20. That's a normal vision. Not all eyes do a good job, and some eyes, for example here, will not refract the light enough so that the rays of light come together at a position in front of the retina, and that's what we call having myopia. Some of the eyes may be too short or will not bend the light enough, and so the point of focus would be behind the retina, so it'd be fuzzy at the retina, and that's hyperopia. Some eyes bend the lens in very different directions, so which is no good, and that's what we call astigmatism. And with age, in fact, pretty much everybody who are 45 years and older end up with presbyopia, which is the fact that your lens becomes a bit less efficient at bending the light enough. So basically, the point of focus is behind the retina, so you see blurry, and you need reading glasses after 45 years old. Okay, so just as information here, when you go to the optometrist and they tell you you have 20/20, what that means is that most people, for example, could read this line here in underlined in red when they're 20 feet away from it. And so can you. So you're like everybody else. At 20 feet, you read what most people will read at 20 feet away from it. If you have an acuity, let's say of 20/70, then you're not so good because, for example, the letter TOZ here, most people can read that size of letter when they're 70 feet away from that chart, but you need to be much closer. You need to be at 20 feet. So your visual acuity is not so good. You need to be closer to read the same thing as people read much further away. Of course, having poor visual acuity is, we can correct that. So you can wear glasses and improve your acuity tremendously to 20/20 easily. So that's okay. So once the light has reached the eyes and reached the retina, it will be transduced. That means that photoreceptor will absorb this light and change it into some neural activity that will travel into the cortex. So here on the left is an eye, and I will show you an enlargement here of this little rectangle. So you can see that at some area that is enlarged there, the the eyes has a point where the blood vessels are gathering, and also axons of neurons are gathering there to form the optic nerve. That area is called the optic disc. And here's a different view of that area. So this is what an optometrist see when they take a picture of your eye or when they look at your eyes with their flashlight. So this area there where you have blood vessel gathering together is the optic disc. And we have no photoreceptor at that position, so we have a blind spot. Around this area, as you can see on the left, you have photoreceptors. And notice on the picture on the right that there's an area where there's no blood vessel coming there. And that's interesting. This area is in fact the fovea. And the fovea is the point of the retina where you have most photoreceptors, where you see best. And that is the point at which the light falls when you fixate on something. So whatever you pay attention to the light will be absorbed from the photoreceptor at the fovea, surrounded in fact by the macula. Here's a more schematic view of the eye, where you see the artery and the veins, and you see the optic disc where all the blood vessels gather together, and we have no photoreceptor at that point. And you see the fovea there where there's no blood vessel right in front of it. And just surrounding the fovea is what we call the macula. And these areas is where we have most photoreceptors. So in fact, at the fovea, we have about 4,000 cones, so that's a lot. And the cones are the photoreceptors that are active during daylight, and we have no rods at that point. The rods are the ones that are active in very low light. So at that point of the fovea, we have the highest visual resolution, and that is where the image at which we look directly is refracted onto the fovea. So whatever you pay attention to will be imaged by that area of your retina. So this is the point where you have best visual acuity, you see details, you have high resolution, the sharpest vision. So as an interesting fact again, unfortunately, some people will age, their eyes will age poorly, and about 12% of people who are 80 years old and older will have a degeneration of the macula under fovea. So sadly, these people will lose vision in the exactly at the location that they want to pay attention to. So they have poor central vision. In this example, let's imagine this is a picture of family members, and the grandmother wants to look at her grandchild. If she stares directly at his face, it will be blurry and she will not see it well if she has macular degeneration. Here's now how the photoreceptors are distributed along the retina. So on the top there, you have an eye. And again, we are taking, say, the retina and flatten it out so that you end up with here on the x-axis, uh, you end up with the retina flatten out. On the y-axis, you have the number of photoreceptors at that position. So first, notice the blind spot where all the blood vessels gather is this point here. And you have no photoreceptor at that point. So you're blind at that point on the retina. Now, this is the fovea. The 0 is the fovea where you have best visual acuity and where most cones are. And cones are the photoreceptor involved in bright light. And as you can see in this graph in blue, most are at the fovea, only few are in periphery. And we have about 4.5 million of them. And the rods are the photoreceptors that are involved in very low light. So at night when you're outside, your cones there's not enough light for the cones to be stimulated, but there is for the rods to be stimulated and active. There are many more rods, about 91 million, but notice that there are none at the level of the fovea, and they are all in periphery. So here's a little experience where you can find your blind spot. So I will tell you what to do right now, but I encourage you to later on come back maybe to this part and do it at your own pace. So the idea here is first, you need to close your left eye. Second, you're going to hold your two hands up with the index finger sticking out so you can stare at one of them. So with your right eye, you're going to look directly at your left hand index finger. So at the equivalent of the red cross there. And I'm going to make you move your right hand index finger sort of left and right. And at some point, at one location there, when you're moving it, it will seem to disappear. And this is the point where the light coming from your finger will fall on your blind spot, right at the level of the retina where you have no photoreceptor. So you're actually moving your eye in and out of the blind spot by going left and right. And the very location where you notice it disappearing is when the light reaches that um, blind disc. So here's another experience that you should try to do where you can have an experience that will show you the distribution of your rods and cones and their light sensitivity. So I'm going to ask you to go stargazing. So while you're out there at night, you will look directly at a star. You will fixate on one star. It will disappear. If you look a bit at it sideways, it will reappear. And why is that? Is the question. And the answer is in the distribution of your rods and cone and their light sensitivity. So we'll come back to that. But first, go out there, try this, and see what happens. So two of the functions of the eyes of refraction and light transmission are really identical to that of a camera, but the eyes are so much more than a camera. So here's an example where your brain can actually create images that are not there. So if you look at this triangle and a sphere there, they are not drawn. Your brain makes them up. So these contours are an illusion, but they're really there and they're really real. Yet there's no stimulation in your eyes for making up these contours. Here's another famous example where with the Necker cube. So if you look at this cube, especially if you close one eye, it is obvious that different people see the same image, that same cube, very differently. Some people will see the the front being the back and the back being the front. And we know that depending on our conditions, it may be more or less easy to flip this cube. So, for example, people who drink a lot of coffee seem to be people who can flip this cube more easily than others. So clearly, for the same retinal stimulation, we can have quite different percepts. So there's something more than just taking the picture here. So as a conclusion, I want to tell you that the eyes are part of your brain. They're your brain. They must transmit enough light so that you afford good vision. They refract light, so they bend light so that it ends up at the level of the retina. You will have detailed vision at the place of the retina where you have most photoreceptors, i.e. the cones here, and that's the fovea. You will see less detail where you have less photoreceptor, and that's in periphery. So in periphery, we have few cones and more rods. The eyes transduce the light into some neural activity where the photoreceptors absorb the light and will send information through the optic nerve to the brain. And we'll see that process some more later on. And we saw that the eyes are much more than a camera. Sometimes you see things that are not even part of the stimuli that are on your retina. So I hope you enjoyed this, and next at our next meeting, we'll talk about stargazing and more of the eyes and visual cortex. See you soon.